Welcome to the Explainer. You ever wonder how an AI goes from making, totally wild guesses to giving you the perfect song recommendation? Well, today we're pulling back the curtain on gradient descent. This is the secret engine, the fundamental algorithm that powers pretty much all of modern AI learning. All right, let's get into it. So, it all kicks off with this really important question. See, AI models, they aren't just born smart. They have to be trained. And a huge part of that training is just figuring out how to get better after making a mistake. So, how on earth does a machine actually learn from its errors? Okay, so how does an AI get smarter? Well, it all comes down to one core idea. You've got to minimize your errors. And to do that, first you need a way to measure just how wrong the AI is. And in machine learning, we've got a special name for that. It's called the loss function. The easiest way to think about it is like an error score. Every single time the AI makes a prediction, the loss function spits out a number. If that number is really high, whoa, the prediction was way off. If the number's low, it was getting warm. So the entire goal, the only goal of the AI, is to get this score as low as possible. It sounds like a simple goal, right? But it's actually a super complex problem. I mean, if a model has millions or even billions of little settings it can tweak, how does it know which ones to change to lower that error score? It can't just guess randomly. That would take forever. It needs a strategy.
And that strategy, that's what we call gradient descent. Honestly, the best way to get your head around it is with a really simple but powerful analogy.
Okay, imagine this with me. You're standing on a hillside somewhere, you're blindfolded, and your one and only mission is to find the absolute lowest point in the whole valley. What do? I mean, you can't see the bottom, but you can feel the ground right there beneath your feet. You'd probably do three things, right? First, you'd feel the slope of the ground. Then, you'd figure out which way is the steepest way down, and you'd take a small, careful step in that direction. And finally, you'd just keep doing that over and over. Feel the slope, take a step. Feel the slope, take a step. This is exactly what gradient descent does. The valley is just our loss function, and those downhill steps are the model tweaking its own settings to make its error score go down. Let's make this even more real. We're going to see how this plays out in a classic example, teaching a machine to predict house prices.
So, on its very first try, the model might be way off. Let's say the actual price of a house is 1 crore rupees, but the model, with its initial random settings, guesses 75 lakhs. That's a huge error, right? Which means it gets a really high score from its loss function. Right now, it's standing way up high on the side of that valley.
And now the algorithm kicks in. It calculates the slope of that error. It's basically figuring out which of its internal settings, like how much importance it gives to location or the number of bedrooms, pushed that guess in the wrong direction. It now knows the steepest downhill path to take to make that error smaller. So it takes a tiny step in that direction, adjusting its settings just a little bit, and then it does it again, and again, and again, thousands, sometimes millions of times. Each and every step is taking it further down into that valley of error. And check this out. Here's the result. After all those tiny steps, the model's new guess is incredibly close to the actual price. The error, that loss score, is now super low. It has successfully walked down the hill and found a spot right near the bottom of the valley. Now, that's a pretty simple example, but here's where it gets really amazing. The real power of gradient descent is that this exact same process is what drives the most mind-blowingly complex AI models we have today. It really doesn't matter if the model is predicting just one number, like a house price, or if it's a massive neural network with billions of parameters trying to recognize faces. The fundamental downhill logic stays exactly the same. The valley just gets way more complex, with millions of dimensions. Now, in a landscape that crazy, there is a risk of getting stuck in a small dip, what we call a local minimum, and thinking you're at the bottom, when the real deepest point is still somewhere else. So what makes this simple idea so powerful? Why is it everywhere? Well, as you can see here, it's just incredibly scalable. It works for huge models and massive data sets. It's also super flexible. Over the years, people have developed smarter versions like Atom and SGD, which are basically just more clever ways of taking those downhill steps, and they help the process go faster and avoid those tricky local minimums. It can even support online learning, where a model literally updates itself in real time as new data flows in. So let's kind of wrap this all up. When you think about AI, you probably picture futuristic robots or these complex digital brains. But underneath almost all of it is this elegant and honestly surprisingly simple mathematical process. This quote right here really just nails it. It's not just an algorithm. For so many things, it is the algorithm. It's the core engine, the unseen backbone that lets machines learn from data and get better and better over time. And you really do see its work everywhere. That system that recommends your next movie? Yep, that's gradient descent finding the lowest error for your personal taste. The facial recognition that unlocks your phone, the navigation in a self-driving car, those incredible translation services, they are all powered by this constant, relentless process of taking small steps to get better. And that kind of leaves us with a final thought. We've seen how this simple downhill rule allows AI to find the bottom of these incredibly complex valleys of air. It is the engine behind so much of our modern world. So, the big question is, what's the next, even deeper valley of discovery it's going to help us find?